So in the previous round, we figured out what the particle in the box wave function had to look like without even barely breaking a sweat in terms of doing any math. But now we want to address this quantitatively. We want to actually know what that wave function is and be able to begin to ask it the questions that we like to ask of quantum objects. So in review, here's our x-axis. There's x equals 0. There's x equals L. And the wave function we already found has to be 0 for x less than 0 because the particle can't be outside of the box, and likewise it has to be 0 for x greater than or equal to L. And then we found that between 0 and L it had to curve up and back down again because the particle had to be there. The wave function couldn't be 0, and as a consequence the wave function has to have curviness because there's only a way to get from 0 at x equals 0 to something at x not equals 0 back down to 0 at x equals L. And I submit that looks a lot like sine. Okay? So let's just give a guess here. We solve a lot of functions by just trying to make an educated guess. And the educated guess here is that sine of x has a lot of what we call salubrious features, like a lot of good things about it. Specifically, sine of x is 0 at x equal to 0. That's actually why we chose 0 at that point, it turns out, but you didn't know that at the time. It's not doing the right stuff outside of the box, but we're just going to prescribe the function to be 0 out there. But inside the box, the wave function sine of x is 0 at x equals 0, and then what does sine do? It goes up and down, and then way down back up, but the up and down part seems pretty good. But we're going to call it sine of lambda x, because if I just say sine of x, I don't have any real control over where it comes back down to 0, and that's going to be the next thing that we have to do. Okay, so here's our wave function again. There's x, 0, and L, and the wave function is 0 outside the box, curves up inside the box between 0 and L, and we're saying that the wave function psi has got to be some normalization factor n times sine of some factor lambda that we don't know yet times x, okay? So now the question is, what is that lambda? What's the value of that lambda, and how do we figure that out? Well, to do that, let's think about sine. Here's x again, and let's just think what sine of x looks like. We go 0, up and down and up and down and up and down and up and down and up and down. It's going to cross 0 at pi, 2 pi, 3 pi, 4 pi, etc. So every n pi, where n is an integer, sine goes across 0. That's what it does, right? So sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, sine of 4 pi, etc., etc., n pi. It's always 0. Well, this gives a hint, because when x is equal to L, we want to be in that very first 0 between the whole wave function that we've been drawing is the same as this function between 0 and pi. So when x is equal to L, we want lambda times x to be pi, or n pi, more generally. We're solving this for n equals 1 for the simple case, but in general, we need that wave function to get to 0 at x equals L. And so any of these nodes, any of these values of n pi will actually work. So for the n equals 1 case, we're going to be right there at lambda times x equals n pi equals just pi. But again, for the general case, any of them will do. So we're going to do lambda L when x equals L is equal to n pi, right? So we just substituted x and L because it's when x equals L that we have to have the value of n pi. So that's going to tell us what lambda is. We can easily solve for lambda. Lambda is just n pi divided by L. Just simply solving that equation. And this is true when x equals 1, 2, 3, 4, blah, blah, blah. X equals 1 is this case of the lowest energy wave function that we've been drawing and figuring out intuitively, but we've also got n equals 2, n equals 3, n equals 4 that we show here in green, purple, and orange. So any of those things actually work on up to infinity. Not just the simple case that we've drawn, but any time that we managed to satisfy that boundary condition by getting this wave function back to 0 at x equals L, we're in good shape. So it turns out we can have a whole lot of solutions to the problem. But the first one, the one with that simple curviness of going up and down again, is the one where n equals 1. Now let's summarize this very carefully because it's really important. Here's our x-axis again. There's x equals 0. There's x equals L. And we're going to draw the ground state wave function. Wave function is always got to be 0 outside of, for x less than 0, and x greater than L outside of the box, and then the ground state just goes up and back down in our nice little sine function that we know it now is. So the wave function psi of x is equal to some normalization constant n times sine, now we can substitute in for lambda, of n pi x divided by L. For n is equal to 1, 2, 3, 4, 5, 6, all the way up to infinity, any integer, any positive integer value, when x is between 0 and L. The wave function psi of x is equal to 0 for x less than 0 and x greater than L. That now is the full description of the wave function. So we haven't figured out the normalization yet. We're going to do that. But we've specified the function. We've got this thing n in there. We specified the value of n. And then because it's this, the function has different forms in different parts of the space here, we've specified that that value, sine n pi x over L, is valid for x between 0 and L. And then we specify as well that the wave function is equal to 0 for values of x outside of that, x less than 0, x greater than L. You got to do all of that to fully describe the wave function. So the really important thing here is we only have solutions for specific values, for certain values of n. We can't pick any old n. It has to be an integer. And that the lambda value we were trying to find only works when n is an integer. So that's why we indicated n equals 1, 2, etc. up there. This is what we call quantization. Instead of any old continuous value, we only have certain discrete values. And that's what we mean when we say that something is quantized. N is, in fact, what we call the quantum number. So when we specify these things and we refer to a quantum number, in this case n, it's going to be that value, usually an integer, that specifies the specific solution, in fact, what we call the specific state of the system. So every wave function is going to turn out to be associated with a thing we call a quantum state, and that quantum state, in turn, is going to be exactly and completely specified by the quantum number. So if we know the problem, and we know the quantum number, and we're talking among ourselves, actually all we have to say is the quantum number, and then we understand all of the rest. I'm not going to let you get away with that on an exam, because you've got to describe the whole thing. But there's a one-to-one correspondence, a unique association between that quantum number and that specific wave function there. When we introduced the Schrödinger equation, which is where the wave function psi of x showed up, we said that what it was built around was figuring out the kinetic energy of the wave function and the total energy of the wave function. And that's where we developed our idea of curviness. So now that we know that psi of x is equal to some normalization times sine of n pi x over L, this is equal for this is for the values of x between 0 and L and any quantum number, integer quantum number n, let's figure out what the energy is. So we've got n equal 1, 2, 3, etc. here. So what is the energy of this particular wave function for a particular value of n? Well, let's apply the Schrödinger equation. Minus h bar squared over twice the mass times the second derivative, d squared over dx squared of psi of x, plus the potential v of x times psi of x, is equal to that total energy E, which is what we want to figure out, times psi of x. That's the Schrödinger equation. All right, well, right away we can cut away this v of x psi of x term, because for the part of the wave function that we're interested in, where the wave function is doing anything interesting at all, where it has any curviness that will identify an energy, the potential is zero. So that just gets rid of that term there. That makes this rather easier. Now let's actually work out the second derivative. So first of all, if we're going to get the second derivative, we've got to get the first derivative. So d by dx of psi of x is equal to n pi over L. That kind of poops out of the sign there when you take the derivative, remember, back from calculus, times n. The sign turns into a cosine of n pi over L times x. Okay, well now let's take the second derivative. D squared over dx squared of psi of x is equal to, now we get another n pi over L pooping out here. So we have n squared pi squared over L squared. The n sticks around. When we take the derivative of cosine, a minus sign pops out as well. We go back to sine, and then we've got n pi x over L there. So the second derivative of the wave function is equal to minus n squared pi squared over L squared times capital N, the normalization constant, times sine of quantum number n pi over L times x. And look at that, n sine n pi over Lx. This is equal to minus n squared pi squared over L squared. And the rest of that stuff there, that's just the original wave function, right? So that's just psi of x. And most important, remember when I said that normalization often just kind of disappears. So that big normalization constant capital N just kept kind of riding along as we were taking derivatives. And then we looked at the resultant from the second derivative there and said, huh, that's our original wave function. And we needed the n in there to do that. So that all turns into psi of x again. And that normalization constant capital N is just kind of gone. We never needed to know it to find out what the total energy is. And that's because the total kinetic energy is equal to the curviness, which involves the second derivative divided by the function itself. So that normalization constant is just going to float on out, and we actually don't have to worry about it to figure out the kinetic energy. All right, hang on here. This is actually kind of cool. So let's just look at what happened here. We took the second derivative of the wave function, and we got back minus n squared pi squared over L squared times the wave function. We took the second derivative, we operated on the wave function, and we got back something times the wave function again. It's not so obvious that that should always happen, but it certainly does work for sine, and it works for cosine as well, in fact. We operated on the wave function, we get back the wave function again, and it just happens to have some extra bit multiplying it on the front, right? But basically we chew on the wave function and we get it back times some number. That's a really important deal. That number that we get back is called the eigenvalue of the problem. So this is an eigenvalue problem. That's German, and the eigenvalue is that number that pops out from the operation that multiplies the original function. So you only have special functions that you can operate on with a particular operator and get back the same function again times some value that we call the eigenvalue. So we call these things eigenvalue equations. This is really, really important because it's going to turn out to have everything to do with the way that quantum mechanics goes about asking questions of the object or the particle of the system. Remember, the wave function is the particle, it is the object, it is the system. Once we specify a potential, we get this solution to the Schrodinger equation, we get a wave function out, and these situations where we have eigenvalues, where we can operate on the wave function and get back the same wave function just multiplied by a number, are the central feature of the entire subject. So let's take this wave function, this eigenfunction that has an eigenvalue, and plop it into the Schrodinger equation. So we have minus h bar squared over twice the mass times the second derivative of the wave function. There's no potential here in this problem. So that's minus h bar squared pi squared over 2ml squared from our second derivative times n squared times psi of x. That's our wave function, and we've added in the h bar squared over twice the mass from the Schrodinger equation. The two minus signs have killed each other, and that's equal to the total energy times psi of x again. Again, remember, the v equals 0 part eliminated the potential energy part of the Schrodinger equation. Well, that simple equation now, I've got this whole eigenvalue thing here. Multiplying the wave function is equal to the total energy E times the wave function. So it's pretty darn easy to solve for E there because I've got the wave function on both sides. I can just divide it out. So the total energy E is equal to h bar squared times pi squared over twice the mass times the length squared, 2ml squared. All that times this quantum number n squared. That's true for any value of the quantum number. N equals 1, 2, 3, 4, 5, etc. on up to infinity. But it's only true for those values of the quantum number. So energy has to be one of these numbers. These are the only solutions. It only works when n is that allowed value, that integer. So it only works for those special eigenfunctions, because remember, there's a one-to-one relationship between n, the quantum number, and psi, the wave function. And because n is telling us what the energy is here, that means that there's only special certain values of the energy. These things we call eigenvalues. So the energy is also quantized. The wave function is quantized, the quantum number, n, gives the energy. And those energies we call eigenvalues in the trade. So in quantum mechanics, we can't have any old energy. We can only have certain special energies for these time-independent stationary solutions here. And they're specified by this quantum number n. And every system we look at is going to have a special set of energies. It's going to have an equation defining the energies, and there's going to be a quantum number associated with that value. As we get farther into the course, we're going to have other quantum numbers cropping up as well, but there's always going to be one that's associated with energy. It's called the principal quantum number. It's sort of the top chicken in the chicken coop, top of the pecking order. That principal quantum number is going to tell us about the energy, and it's always, always, always going to be quantized.